Hey everyone, welcome to Lecture 6. Today we're going to be focusing on cardiac output. I have the sick guy here with me, so hopefully he cooperates and takes a nap at some point so I can get this video recorded for you. We're going to be talking about cardiac output, which is how much blood is moved by the ventricles within the heart, the output of the heart, cardiac output. And specifically, we're going to be spending most of our time talking about control of cardiac output. All right, so without further ado, let's get going. You can access Worksheet 6 on Canvas, and there's also a list of objectives and vocabulary that you can print off as well. All right, our objectives for today. The first thing we'll do is we'll look at the determinants of cardiac output, or CO. We'll then look at the effects of both parasympathetic innervation and sympathetic innervation. And then we'll look individually at control of heart rate, followed by control of stroke volume. And with control of stroke volume, we're going to talk about intrinsic versus extrinsic control. And as always, we have some memes to kick us off. This is a fellow professor. I'm not sure at what institution, but he's getting real personal with his students. Cardiac output is the amount of blood that's going to be pumped by each ventricle in a given amount of time. So the components of cardiac output, or CO, are heart rate and stroke volume. So recall when we initially started talking about all this, we said the role of the cardiovascular system was to provide adequate perfusion to the tissues. Well, cardiac output is going to be the determinant if we're adequately perfusing tissues or not, right? We need proper cardiac output, heart rate and stroke volume, in order to deliver oxygen to those tissues. Now, cardiac output is measured in mils per minute, heart rate is BPM, beats per minute, and then stroke volume, or how much blood is being ejected from the ventricle, is in mils per contraction, or mils per beat. Let's take a quick break here, just to make sure we're all on the same page and do some very simple math. So I'm saying here, determine cardiac output using the given information here. The average heart rate for this individual is 70 beats per minute, and then their stroke volume is 70 mils per beat. So then determine cardiac output for this individual. Well, it's pretty simple math, but let's just make sure we're understanding what we're looking at. So cardiac output is the heart rate multiplied by the stroke volume. So the heart rate, again, is in beats per minute. So it's how often it's beating. And then stroke volume is the volume of blood that the ventricles are moving. So we multiply those two together to give us the total output of the heart, the cardiac output. So we said that this person had a heart rate of 70 beats per minute. And then with each contraction of the ventricle, we're moving 70 mils. So we multiply those together, and we get 4,900 mils per minute once we cancel out the units. Okay. So we know that there's 1,000 mils per liter, so this comes out to 4.9 liters, or about 5 liters of blood those ventricles are pumping per minute. And this is impressive because that means that the ventricle is moving the entire volume of blood within your body over a minute. And that's just your resting heart rate, okay? Because the average body has about 5 liters of blood, and that's what we're pumping within a minute. Now, resting cardiac output is going to vary from person to person. So for example, individuals that have smaller hearts, we're going to see that they have smaller stroke volumes. Now, to wrap your mind around this concept here, how would a person compensate to maintain a normal resting cardiac output if they have a smaller heart and a smaller stroke volume? Okay, well, you might have arrived at this conclusion that they must have a faster heart rate, right? Those are our two components of cardiac output, their heart rate or stroke volume. So if you have a reduced stroke volume, you got to compensate for that by increasing your heart rate. And on average, we see that women and children have smaller hearts than men and therefore have faster heart rates on average. Okay? Now, individuals with larger hearts, we would see that they have a larger stroke volume, and therefore they can have slightly slower heart rates. They're moving more blood with each contraction of the heart. So for example, endurance athletes, they're going to have larger and stronger hearts, and therefore slower resting heart rates and lower, Here are some of those resting heart rates that we would see throughout our lifetime. So you can see there's quite a range, right? With babies, those hearts are so small, they need to keep a higher rate, so 140 beats per minute. Okay? Now we can compare that to a full-grown adult male, and that average resting heart rate can be around 60 beats per minute. So there's a large range there, and that's based on heart size. And smaller hearts, we need to have higher heart rate to keep up appropriate cardiac output. So we said that on average, under resting conditions, we see that cardiac output is around 5 liters per minute. But what if we increase our physical activity? What happens then? Well, you guessed it, cardiac output is going to increase as well. And in fact, with an increase in physical activity, we can see cardiac output reach levels such as 20 to 25 liters per minute. Now, to give you some perspective, a 5-gallon water cooler, that's actually a little less than 19 liters. Okay? So really, we're moving, in a minute, the equivalent of a little more than one of those 5-gallon water coolers of blood when we're at the peak of our physical activity. And it even gets more impressive than that. And in competitive athletes, we can see that cardiac output reach as high as 35 liters per minute. Right? And that, again, is going to be due to a product of stronger contractions of the heart, and they have larger hearts as well due to hypertrophy of those heart walls. So larger heart, stronger contraction, greater stroke volume. They can move more blood efficiently, about 35 liters per minute. So that's really impressive. All right, now let's talk about cardiac reserve. And when you hear reserve, you kind of think about the extra ability of something, right? It's like a little extra we could tap into should we need it. So when we're talking about cardiac reserve, we're talking about the capacity of the heart to increase cardiac output above its resting level. So how much higher can we go from resting level with our cardiac output? So heart rate accelerates and stroke volume are going to increase during exercise. Okay? And then therefore our cardiac output is going to increase as well, right? Because heart rate and stroke volume are components of that. So then effectively what cardiac reserve tells us or gives us is a measure of the level of activity that we could pursue. So how far can we take it beyond our resting capabilities? What can we get our cardiac output up to? What is our reserve? So for example, to apply this, cardiac output can increase up to 4-fold in someone like me. I'm healthy. I'm not an athlete. Well, I don't know, it's a little bit of cycling, but I'm nowhere near a competitive athlete. But that can increase up to 7-fold in our top athletes. So cardiac output increasing by 7 times from resting in your top athletes. Okay? But I want you to think about this then. So how can cardiac output, which is a determinant of heart rate and stroke volume, how can cardiac output vary so much depending on activity? Well, you might have said the autonomic nervous system, and in which case you would be correct. So it's important to remember that the heart rate is initiated by the sinoatrial node, the SA node, right? That's the typical pacemaker of the heart, and it's that clustering of autorhythmic cells. They spontaneously depolarize without other nervous input. But we can change the heart rate and contraction strength with autonomic input. Okay? So sympathetic, parasympathetic innervation to the heart. That's going to be regulated by the cardiac center within the brainstem. We'll look at that in a second. And we can alter our components of cardiac output, like heart rate and strength of contraction. Okay? there's our SA node that is typically pacemaker of the heart. These are going to spontaneously depolarize, these autorhythmic cells, spread through the heart to give us our kind of basal rhythm of the heart. We can change that given a parasympathetic or sympathetic response. Going back to basics, when we're talking about that autonomic innervation of the heart, we would see that the parasympathetic innervation, that is going to decrease the heart rate, right? Rest and digest. A sympathetic response, sympathetic innervation, is going to increase heart rate, fight or flight. And also, it's going to increase the force of contraction, or therefore the stroke volume. So let's take a look at how this works. All right, within the brainstem here is the medulla oblongata. And if you remember, the medulla and the brainstem, they take care of a lot of our different autonomic functions. So within the brainstem here, we have the cardiac center, and it's comprised of both a cardiooscillatory and cardioinhibitory center. These are appropriately named because the cardiooscillatory center is going to act to increase heart rate and contractile force. Cardioinhibitory center is going to act to decrease heart rate only. Okay, so let's take a look at this. Next up, you should know these nerves. We have the vagus nerves. And the vagus nerve, I've kind of color coordinated this here, so that's going to be shown in orange. The vagus nerve innervates the heart and is going to send cardioinhibitory signals via that parasympathetic pathway, the vagus nerve. So we can decrease heart rate in that manner. Okay. Cardiac nerve is going to do the opposite here. Here we're going to be sending cardiooscillatory centers from that cardiooscillatory center in the brainstem to the heart. Okay? And in that manner, we can increase heart rate and increase the force of contraction. And we'll talk about how that increase in force of contraction is possible shortly. Okay? Now, the last component here are these receptors. So there's different baroreceptors, so they detect pressure, or chemoreceptors, detect different chemicals within the bloodstream. And if we were to shift away from our norms, those receptors can inform the cardiac center within the brain to tell us whether we need to activate a sympathetic response via the cardiooscillatory center or a cardioinhibitory center for a parasympathetic response. Okay? First, let's look at the effect of parasympathetic stimulation. So here we're talking about signals from that cardioinhibitory center. Well, the first thing we're going to do is we're going to decrease the depolarization at that SA node. So stop firing of those action potentials at such a quick rate. So we're going to slow that down. And we do that by increasing this drift to threshold here with those autorhythmic cells. So remember we had those funny channels, right? One of the ion channels we talked about. Well, we'll look at the specific effects of the ion channels in a second, but what we can do is we can slow this drift to threshold so we hit threshold less often. Okay? The other thing we can do is we can increase our delay, or that we do is increase the delay at that second node, the atrioventricular node, the AV node. And you can think, if we're slowing the rate of the heart, we also have to increase the delay at the AV node to proportionally space out the atrial and ventricular contractions. So we decrease firing at SA, we increase delay at AV, and we also see here that with a parasympathetic response, we do not see effect on the ventricular contraction. So the force of the contraction does not change much. Here we see the membrane potential of our autorhythmic cells. Okay. So if we focus first on that black dashed line, that's going to represent the typical SA node pacemaker activity. Okay? And that red is going to represent after parasympathetic stimulation. So you can see where as we hit threshold twice before with this normal rhythm of the heart before parasympathetic innervation, once we have parasympathetic innervation, you can see a couple things. We hyperpolarize more, so you can see we're going past negative 60 here, maybe down to negative 70 or so. So we're becoming more negative. we're also prolonging this drift to threshold. By prolonging this drift here, this pacemaker potential, we're going to hit threshold less often, okay, and get less action potentials, therefore less depolarizations, less contractions. So where we hit threshold twice before, we're only hitting it once here for a single actual potential in this autorhythmic cell. So we've slowed the heart rate. With a parasympathetic response, we see this decrease in heart rate, and that's going to be the product of acetylcholine binding muscarinic receptors on those autorhythmic cells, the clustering of autorhythmic cells within the SA node, right? So those are going to spontaneously depolarize, but we can alter their behavior with this parasympathetic neurotransmitter acetylcholine. So let's turn to the figure here. So we see this acetylcholine. That's going to be released from that vagus nerve, from the cardio-inhibitory center within the brainstem. That's going to bind this muscarinic receptor, which is a G protein coupled receptor. And ultimately, upon activating this G protein, what we do is we increase potassium channel permeability. Okay? We'll look at which specific potassium channel in a second. But what we see then ultimately is we alter our pacemaker potential. So going back to this membrane potential figure we just looked at. And we see we both hyperpolarize now due to this increased permeability of potassium channel, and we elongate this drift to threshold. Okay? Because we hit threshold less often, fewer contractions, we've effectively decreased our heart rate with this parasympathetic response. Just a quick review, if you turn to the board drawing we did of the membrane potential of the autorhythmic cells, the cells that make up the nodes that spontaneously depolarize. So remember, we have our funny channels that open upon hyperpolarization, so they're funny, and that leads to a slight depolarization. Then we get these T-type calcium channels that open up in response to that. And then eventually we get these L-type calcium channels that give us this large depolarization. Okay? Well, once those close at the top of this depolarization, that's when our voltage-gated potassium channels open. And these now are the voltage-gated potassium channels we're talking about that increase, or decrease, I should say, this drift to threshold. Basically what happens is we've increased the permeability of these voltage-gated potassium channels, right? That is what that acetylcholine and that activated G-coupled protein have done for us. So what happens is they're open longer. So you can imagine if they're open longer, we're going to hyperpolarize. We're going to go even more negative than we did before. And that elongates this drift to threshold, which slows our heart rate. All right, let's compare that now to the effect of sympathetic stimulation. So this is going to be the cardio-oscillatory center, okay, and its sympathetic effect on the heart. And what we're going to do here is we're going to increase the depolarization of those autorhythmic cells. So we're going to increase the firing of the SA node. They're going to depolarize more often. So we're going to be shortening this drift to threshold here. So we hit threshold more often. Then we're going to want to reduce the delay at the AV node here so we can have our ventricular contractions follow our atrial contractions more closely. And then the last thing we're going to do that is a new component here compared to our parasympathetic response is we are going to have effect on the ventricular contraction. We're going to have a stronger contraction as well, not just change the rate of the heart here. So similar to before, we have our membrane potential here of an autorhythmic cell. So maybe these are the autorhythmic cells that make up the SA node. And we can see that black dashed line. And again, that's going to be just the normal depolarization rate of those autorhythmic cells of the SA node. So you can see here we got 2 depolarizations within this time frame. Now, if we have a sympathetic response, that's going to increase our rate of depolarization. You can see now we shorten this drift to threshold. It's very steep. So we're hitting threshold 3 times in this time frame, giving us 3 contractions, whereas before we only had 2. So we've increased our heart rate by shortening that drift to threshold. So we see with a sympathetic response an increase in both heart rate and contractile force, which means an increase in stroke volume. Okay, so how are we doing this? Well, there's that cardiooscillatory center within the brainstem. And then via the cardiac nerve, we innervate the heart, and that's going to release norepinephrine. Okay, that norepinephrine, if you think back to last semester, it's going to bind adrenergic receptors, and specifically here, we're talking about beta-1 receptors. Remember there were alpha and beta adrenergic receptors? Well, here the beta-1, those are the ones that are associated with heart activity. Okay. If we turn to this figure down here at the bottom, we'll see that our cardiac nerve from the cardiooscillatory center is going to release norepinephrine. Okay, that norepinephrine is going to bind that beta-1 receptor. And again, this is going to be a G protein couple receptor. Okay, so we're going to activate adenylyl cyclase. We're going to increase our cyclic A&P, activating pKa. And what we're going to do then, as kinases do, they're going to phosphorylate a whole bunch of different channels. And specifically here, we're going to increase our funny channel permeability. So that's going to increase our permeability to sodium. We're going to phosphorylate and increase the permeability of our T-type calcium channels. And then lastly, which is not shown, this is a autorhythmic cell, but on our contractile cell, we are going to increase the permeability of our L-type calcium channels. So what does that do? What's the result? Well, we increase this drift to threshold. See how this is a much steeper slope now? And we're going to hit threshold more often by increasing the permeability of these ion channels. Okay, so we're going to increase our heart rate, and additionally, we're going to increase our contractile force. So let's turn to our board drawings and look at how we do that. Here's the board drawing of our autorhythmic cell membrane potential again that we're familiar with. And here we have our funny channel. Remember the funny channel opens in response to hyperpolarization, not a depolarization. So that's why it's funny. Okay? And remember that these are voltage-gated sodium channels. So we're going to see with a sympathetic response, we're going to see an increase in permeability of these voltage-gated sodium channels. Okay? So that means if they're more permeable, we're going to see a greater influx of sodium, right? And that's going to help us hit this threshold more often. We're going to depolarize more quickly. And we're also going to see an increase in permeability of these T-type calcium channels. So same thing, right? With that calcium influx, we're going to hit threshold more often. So this is how we increase our heart rate and hit threshold more often by changing the permeability of this sodium channel and calcium channel. Again, this is looking at our autorhythmic cell here. So we increase our heart rate. But how do we increase the contractile force then of the heart, which is an additional component of the sympathetic response? Okay. Now we're looking at a contractile cell. And you remember this board drawing here? This is our membrane potential of the contractile cell. Okay. And what we see then with a sympathetic response, when that epinephrine is released from that cardiac nerve, it's going to affect the permeability of those L-type calcium channels on our contractile cell. So the previous two effects we saw were looking at the autorhythmic cells. Now we're looking at contractile. And what we're going to see here is they increase the permeability of those L-type calcium channels. So they're going to be open longer. If they're open longer, we're going to see more calcium moving into that cell. So here's a view of the cell membrane of our contractile cell. So let's just review. Norepinephrine is going to be released from the cardiac nerve, from the cardiooscillatory center. It's going to bind a beta-1 adrenergic receptor. This is a G protein coupled receptor. So that activated G protein is going to go along, and ultimately what we're going to do is we're going to increase the permeability of this L-type calcium channel. If we increase the permeability, we're going to see an influx of these positively charged calcium ions. And here, these are the contractile cells. So we know what calcium does when it enters this cell. Okay? We're going to have calcium-induced calcium release, and then some of that calcium can go and bind directly to troponin, and then pull that tropomyosin away and lead to an increase in cardiac muscle force, right? We've increased the force of our contraction. Let's compare this to our board drawing just so we're making sure we're making complete sense of this. This is a board image from class, and it's really another way to look at the previous slide in a slightly different way. So here we have our L-type voltage-gated calcium channels that we just saw in the previous slide. They're going to be located within this transverse tubule, right, on the contractile cell. So here's our L-type calcium channel. That depolarization can lead to an influx of calcium, right? These are more permeable now due to the activation of those beta-1 receptors, right? So we're going to see increased permeability of these calcium channels, so we're going to see increased calcium influx. Then you're going to have to think back. This is going to lead to calcium-induced calcium release. Some of that calcium is going to go and bind directly to troponin. Okay? It's going to pull that tropomyosin out of the way and lead to contraction. But some of that calcium is going to go and bind the ranitidine receptors on the endoplasmic reticulum and lead to even more calcium release. Okay? So again, this is going to increase the force of our contraction. So this is how, with a sympathetic response, in addition to seeing increased heart rate, we also see an increase in contractile force. Now that we've reviewed autonomic innervation of the heart and the effects, I want to say a little bit more about determinants or control of heart rate and stroke volume. So let's start with heart rate here, one of our components of cardiac output. Again, this is the first determinant of cardiac output, is heart rate. Now, agents that affect the heart rate, they can change it, either speed it up or slow it down. We call chronotropic agents. And this is somewhat easy to remember because that prefix chrono means time, right? Like chronological order. So this is done. We can change the heart rate or the speed of the heart by altering the activity of the nodal cells that we just saw with sympathetic and parasympathetic innervation. We also saw that this is done via the autonomic nervous system. So for example, we're talking about a sympathetic response. That's going to be norepinephrine, or the epinephrine that is released from the adrenal glands. Okay? So we can have agents that increase the heart rate, and we call those positive chronotropic agents, or we can have agents that decrease or slow the heart rate, and we call those negative chronotropic agents. So here I'm just defining some new terms and applying it to the things you've already learned today. Now, just as an FYI, we've kind of talked about how the resting rhythm of the heart, or the rate, is around 70 beats per minute. And we've been saying that that's without autonomic input. That's not exactly true, because under resting conditions, the parasympathetic nervous system dominates. So these are the effects of acetylcholine, right? So we're going to be suppressing sympathetic response in those situations, the norepinephrine. So actually, what we would see if you were to block autonomic innervation completely to the heart, including that parasympathetic innervation, the resting heart rate increases to about 100 beats per minute because we don't have that parasympathetic dominance. But when we add in that parasympathetic control, that's what brings our resting heart rate down to about 70 beats per minute. So that's kind of just an FYI. just so you know in case that comes up. Under resting conditions then, our heart rate is going to be under parasympathetic influence, and we can alter that in either direction with these different chronotropic agents, right? We can have acetylcholine or epinephrine. We can alter it in either direction by shifting that balance of autonomic input. So we can speed it up by increasing the sympathetic response while decreasing parasympathetic, or vice versa. Right, let's finish up today then by talking about that second determinant of cardiac output, stroke volume. Now, when we change stroke volume, this is going to be due to inotropic agents. Okay? So inotropic agents, such as epinephrine or norepinephrine, we saw that they were able to alter contractility. So contractility, that's a new word for us. That just means the force of that contraction. And the harder we contract, right, more forceful contraction, that's going to increase our stroke volume. And as we saw with the effects on the contractile cell of epinephrine and the increase in permeability of those L-type calcium channels, that leads to more calcium available within that contractile cell. And that is going to increase the number of cross bridges are formed, right, within the sarcomere. So we're going to have stronger contractions. So there's both positive and negative inotropic agents. So positive inotropic agents then are going to increase the amount of available calcium within those contractile cells. And that's going to lead to that more forceful contraction. So you can imagine, let's say you need to increase the contractility of your heart for some reason. Well, there's certain drugs like digitalis, they're going to increase the calcium within that contractile cell and leading to a more forceful contraction and therefore greater stroke volume. Negative inotropic agents, on the other hand, are going to decrease the amount of calcium within that cell. And maybe you've heard of calcium channel blockers, right? So these drugs are going to block those L-type calcium channels and lead to less calcium being available within that cell and therefore decrease contractility, decreased stroke volume. All right. So I want to finish up today by talking about control of stroke volume. Okay? And there's two ways we control stroke volume within the heart. Remember, that's the amount of blood being pumped by the ventricle with each contraction. And the way we control stroke volume, it can either be intrinsic control or extrinsic control. So that word intrinsic, that's just a fancy way of saying it's kind of like this built-in inherent ability of the heart to vary its own stroke volume. And it's going to be related to venous return, or how much blood is coming back to the heart from systemic circulation. Okay, we'll go into detail here in a second. Extrinsic control, that's going to be what we reviewed already. That's going to be the extent of sympathetic stimulation, right? That's going to be that cardiac nerve releasing norepinephrine, leading to increased permeability of the L-type calcium channels, more calcium in that cell, stronger contraction. Let's start by looking at this intrinsic control, since that's a new concept for us. Well, we said that intrinsic control of stroke volume is related to the extent of venous return. So what do we mean by that? Well, venous return is the volume of the blood that returns to the heart. So it's going to determine the amount of blood in the ventricles prior to a contraction, right? If you have more blood returning to the heart, there's going to be more blood in the ventricles. So that means a higher end diastolic volume. We just reviewed that last class. That is the amount of blood, or the volume, at the end of diastole. So it's how much we filled that ventricle. And that EDV, that amount of volume after filling the ventricle, determines the preload. So there's a new word for you. You may hear some of the instructors use this in lab. Preload, all that means is the pressure that's stretching the heart wall before the shortening of those contractile cells. Now, if you recall back to last semester when we talked about this length tension curve within skeletal muscle, remember that there was kind of this optimal length, this resting muscle length, where we get a maximal contraction or tension, right? And if you deviate from this optimal resting length, we see decreased tension or contractile ability. And again, that has to do with your sarcomeres here, right? So if they're stretched out, then you have less interaction of myosin heads, right, with the thin filaments, the actin. Okay? And if you compress them too much, same thing, less interaction between them. So there's this optimal length for skeletal muscle where you get optimal interaction of myosin heads and the actin molecules on the thin filaments. Okay? But there's this very small range. Well, that's not the case with cardiac muscle. And I'm going to introduce Starling's law to you now, which is going to come in handy for lab this week when we look at the grass frog heart. Now let's compare that to the length tension curve for cardiac muscle. Okay? So notice we have similar terms. Here we have our length and our tension then on our y-axis. And notice we're calling them slightly different things. Here we have end diastolic volume, and that's going to be analogous to length. So remember, your EDV, or end diastolic volume, is how much blood is going to be in that ventricle after filling. So this is going to determine the length of your sarcomere, right? Imagine you're filling that ventricle with more blood. That's going to change the length of that sarcomere, okay? Now, on our y-axis, we have tension or stroke volume. So this is going to be the contractile force, basically, or how much blood we're able to eject, okay, with each stroke. Okay, let's turn to this figure here. Here is our normal resting length. So let's say resting heart condition, and we're going to have some corresponding end diastolic volume with that. Now notice, way up here at the top of our curve, around 300 or so mils of end diastolic volume, this is our optimal length. So this is where we're going to get max contractile force, tension, or stroke volume, right? This is way different from our skeletal muscle. We move out of that range really quickly within skeletal muscle. Okay. So let's look at something here. Let's say we have point A. So we're resting, we have some end diastolic volume, and that's going to correspond to some stroke volume. And then we're going to have an increase in blood returning to the heart. So we're going to have a higher end diastolic volume. Let's say we've started walking briskly. Okay, so we see an increase in end diastolic volume, and that's going to stretch out this sarcomere. So it's an increase in length. So we move up this curve, and notice now we're going to have a correspondingly greater stroke volume. Right? So we've increased our stroke volume. We have better overlap of actin and myosin as we continue to increase tension on this heart by filling it with more blood. And this is Starling's law, and this is just saying that with increased end diastolic volume, the more blood that is returning to the heart, the more full those ventricles are, the more we'll be able to eject that blood. And this is important. More blood's returning, we got to be able to increase our stroke volume to eject it to increase our cardiac output. All right, so let's apply this intrinsic control. So let's say we have an increase in sympathetic activity, right? So what is that going to do? With an increased heart rate, we're going to see an increase in venous return. More blood's going to be returning to the heart. Okay, this is that idea of intrinsic control. It's the heart's own ability to change stroke volume, because with that increase in venous return, we're going to see increase in end diastolic volume. That ventricle is going to be more full. It's going to stretch out those sarcomeres and give us the ability to have increased stroke volume and strength of cardiac contraction. Okay? So that increases our stroke volume, that higher EDV. Okay? So that's intrinsic control. Let's compare that then to extrinsic control. Extrinsic control then is going to involve those inotropic agents we talked about, such as norepinephrine, right? And norepinephrine is going to lead to that increase in calcium release. We're going to bind those beta-1 adrenergic cells. We're going to have a sympathetic effect, which ultimately leads to increased calcium release. That is going to lead to direct increased strength of cardiac contraction, and therefore more blood is ejected. We have increased stroke volume. So you can see then we have this extrinsic control of the heart, as well as this intrinsic control of the heart's stroke volume. Okay, let's put it all together for the final picture. You can complete your worksheet. This is on there as well. So we have cardiac output, right? And we know that this is a product of heart rate and stroke volume. Heart rate can be influenced by parasympathetic or sympathetic activity. Okay? Sympathetic activity can also increase venous return, right? If we increase our heart rate, we're going to have, or in force, we're going to have more blood returning to the heart. That's going to increase our end diastolic volume. If our end diastolic volume is greater, we just looked at this intrinsic control, we're going to have greater stretch of the sarcomeres, we're going to have increased contractile force, greater stroke volume. Okay, that's it. We'll see you in class on Tuesday for review.